Somewhere on the grid right now, there is a short circuit. A storm, a tree, a digger. It happens every day. A circuit breaker has to open and clear that fault. And every breaker carries one critical number, the biggest current it can interrupt. So where does that number come from? It comes from the source, the synchronous generator. Short a generator and its current starts very high, then falls. That first highest value is the number that sizes the breaker. Let's find it. Here is the key idea, and it is one we already know. A generator stores energy in a magnetic field. In that way, it is like an inductor, a coil that stores energy in its own field. And an inductor resists a sudden change in current because its field cannot change in an instant. So, consider a charged coil and then short it. In the first moment, the field is still full, so it drives a large current. Then, the field drains and the current falls away. A generator does the same thing, on a much larger scale. Its spinning rotor keeps the field charged, so we model the generator simply, an internal voltage, call it E, behind a reactance, X, which is its opposition to a change in current. A source and one impedance. This is the same shape we used for the transformer. Now, that reactance is not a single number. Here is why. The current is tied to the magnetic flux, and the flux cannot change in an instant. So, in the first cycle or two after the fault, the flux is still trapped, and the machine shows only a small reactance. A small reactance means a large current. We call this the subtransient reactance, the reactance in the first moments. Over the next several cycles, the flux redistributes, the reactance grows, and the current drops. This is the transient reactance. Finally, the machine settles. The reactance reaches its full value, the synchronous reactance, and the current reaches its steady level. So the current follows one simple rule at every stage. The current is the internal voltage divided by the reactance. The voltage stays the same. The reactance grows. So the current falls. Let's put numbers on it. Take a generator with an internal voltage of 1 per unit. Its datasheet lists 3 reactances: subtransient 0.15, transient 0.25, and synchronous 1.2 per unit. The current at each stage is that voltage, divided by the reactance. In the first cycle, the reactance is small, so the current is large, about 6.7 times full load. A few cycles later, it drops to 4 times. At steady state, it falls to about 0.8, below full load. So, here is why this matters. A circuit breaker has to interrupt the fault. It meets that first, subtransient current, the biggest one. So, we size the breaker for the first cycle, not for the settled value. Get this number wrong, and the breaker can fail when it is needed most. So, the synchronous generator. We model it as an internal voltage behind a reactance, a source, and one impedance. That reactance is not fixed. It grows with time because the flux cannot change instantly. Small at first, then larger, then largest. Subtransient, transient, synchronous. So the fault current starts high and falls. And that first value, the subtransient, sets the rating of the circuit breaker. This is where the generator enters a short circuit study. Next, we connect the machines, transformers, and lines into one network using the admittance matrix, the Y bus. Subscribe, and see you in the next one.